appropriate time. Otherwise, please feel free to ask your questions following the speaker's presentation. All right. Okay, so today is our distinct pleasure to welcome Michael Foss-Feig, coming from Honeywell Quantum Solutions. So Mike did his PhD at the University of Colorado Boulder and the Gila Institute, where he worked with Anna Maria Ray. He was also awarded the DAMOP Thesis Prize in 2013 for quite a wide range of really exciting work that he did. A lot of which was in collaboration with many experiments, including the experiment that I did my PhD on. He then went to NIST and was an NRC postdoctoral fellow, where he worked with Charles Clark and a number of the folks at NIST in Maryland. And then he spent a few years at the U.S. Army Research Lab in Maryland before moving to Honeywell a few years ago, where he's kind of leading a growing theory contribution to their very exciting experimental developments. So please help me in welcoming Mike as this week's seminar speaker. Mike, please go ahead.
All right, thank you very much. Yeah, it's really a pleasure to virtually be there. And yeah, so I take it the idea is to type questions into the chat, but you know, I love getting questions during a talk. It helps me gauge if what I'm saying is making any sense. So please feel free to ask, and Jake, feel free to interrupt me with any question at all. So yeah, so if you've heard of Honeywell Quantum Solutions, you probably think about us as a hardware company, and that's primarily what the effort is. It's roughly speaking, 150 people building quantum computers, trapped ion-based quantum computers. But we do have sort of a relatively small scale theoretical effort, some of which is dedicated to supporting the development of trapped ion architectures and improving gate fidelities, that kind of thing. And then some of which is also focused on identifying algorithms and things that exploit the kind of unique capabilities that we have. And so what I'm going to talk about today is work of the latter type. So it's really talk about an algorithm or a set of algorithms based around classical tensor network techniques, but ported onto quantum computers. And I'll take kind of a brief moment in the middle of the talk just to go into just a few details about Honeywell's actual architecture and why it's a nice fit for these kind of algorithms. And then I should also say this work, so the work that I'm going to be talking about here was really headed up by a really talented intern we had, Ellie Kirchhoff, who actually was a grad student at Illinois when he came over and spent the summer doing this stuff at Honeywell. And so we have kind of a nice internship program. If you are a grad student, or if you're on this call and have grad students that might be interested, feel free to reach out to me. And I think it's a pretty good opportunity for people, either theorists or experimentalists, honestly, to jump into a pretty fast-paced environment and make real contributions. And then if you're interested in more details, a lot of what I talk about will be kind of at a superficial level, but you can see any of these three archive posts for more details about the specific algorithms that I'm talking about. Okay. Now, so with that, let's get started. So, to understand the benefit of classical tensor network techniques and what they really do, you kind of have to start by asking, what do quantum states of physical systems tend to look like? And so here's just kind of a schematic representation of a quantum system. So these are meant to be a bunch of quantum particles. And, these could be qubits. I've kind of drawn them floating around in space as if maybe they're like, neutral atoms in a gas or an optical lattice, but it could really be just about anything. And, if you ask what makes the system quantum, the sort of important aspect of, the quantumness of a many-body system is primarily entanglement, the fact that, quantum degrees of freedom can be entangled with each other. And if you think about kind of, the worst case scenario from the standpoint of how hard would it be to simulate the system, that happens when everything is kind of entangled with, everything else or anything else at any length scale. And so if you can have entanglement over arbitrary length scales, then, that sort of pattern of entanglement drawn schematically would look something like this. And what that would tell you is that if you kind of drew a division through the system and just called like half of your atoms A atoms and half of them B atoms, the extent to which A was entangled with B, quantified by what's called entanglement entropy, would scale with the number of particles, just for the simple reason that every qubit in A is likely to be, kind of 50% likely to be entangled with something in B. And this is really the situation in which the naive guess at how the difficulty of simulating a quantum system scales, which you might guess that it should be exponential in n, simply because that's the number of complex amplitudes you would have to write down to describe a wave function on a many-body configuration space. This is really kind of the limit in which that difficulty is actually present, and you'd expect that difficulty to truly hold. So in reality, physical systems don't tend to look like this. And the reason is pretty simple, right? In a physical system, you tend to have short range interactions between the particles. And you could imagine producing, some low temperature phase of a many body system by starting in a high temperature state where everything is just totally uncorrelated and ramping down the temperature pretty quickly. And you don't expect that to take, macroscopically long, like an extensive amount of time. And therefore, you don't expect entanglement to develop over macroscopic length scales during that cooling process. And so when you get to some approximation of a ground state, entanglement should look more like this. And what that means is that if you draw a division between, the left half and right half of your system, say, the amount of entanglement shared between those halves tends to scale just with the boundary area of this cut. So you may hear people refer to entanglement entropy area laws in sort of a quantum information context. And this is really what they mean, just that the amount of entanglement between the left half and the right half scales like the area of the boundary between those halves. And so in general, this entanglement entropy, this bipartite entanglement entropy, it can be shown under certain types of simulation techniques to control the actual classical hardness of expressing and doing calculations with the state of this system. And because this entropy is only proportional to the boundary area and not the volume, it's generally true for large systems that the entanglement entropy is much less than n. And therefore, the difficulty to simulate this system using techniques that exploit this limited entanglement, so tensor network techniques, is generally much less than you'd guess in the worst case, kind of 2 to the n. And so that kind of brings me to a very kind of coarse description of what tensor networks are. And at the highest level, you can, there's a lot of different flavors of tensor network ansatzes, but they're all just different ansatzes for expressing states of physical systems that tend to be very concise and very useful when those states have limited entanglement. And so there's all kinds of flavors of this, and I'm just going to show a very simple one, which some people may be familiar with, and that is matrix product states. And matrix product states, it's just a subclass of tensor networks that in principle you can use to describe any system you want, but they're really best suited for one-dimensional systems. That's kind of the context in which they were originally dreamed up and which they're primarily employed in classical simulation of quantum systems. And so this is kind of a slightly unusual way to introduce matrix product states, but I'll get to, eventually a tensor network diagram that might look more familiar to people that think about matrix product states in detail. And so in one dimension, this statement that I made about entanglement being kind of localized in space is actually, it leads to a particularly simple structure, right? So if I take a one-dimensional array of quantum particles, so say qubits, and I draw a cut between, in this case, the upper half and the lower half of this system, then in general, you only have entanglement between qubits that are close to that cut on both sides. And in one dimension, what's unique about that is it means that the entanglement entropy is not just much less than the total number of qubits. In general, it's actually finite, even for an infinite system. right? Because if it kind of decays for qubits that are further from the boundary, then even if the system extended up and down forever, the amount of entanglement entropy would be finite. Now, you might guess that you could exploit that kind of limited entanglement to write down an ansatz for a state like this in the following simple form, right? You'd say, well, the top half is only weakly entangled with the bottom half, so it looks almost like it's uncorrelated. And the problem with doing that is that you're more or less throwing the baby out with the bathwater, right? Like the extent to which quantum systems are interesting is basically just the extent to which this approximation is not exactly right. So we need to do a little bit better than this. And it turns out that a good way to build up any system that has limited entanglement entropy is to first create a state just on this half of the system and then entangle it with some ancilla register of qubits, so some other ancillary quantum system. And then you move that quantum system down and subsequently entangle it with this half of the system. And it turns out that by doing that, you can build up any state of this complete system that has small entanglement entropy across this cut. Now, because the entropy is small across every cut, that suggests there's actually an even sort of, there's a generalization of this where you build up the entire state, not just connect two halves. So you start by, talking to just this first qubit, entangling it with an ancilla register, and then you sweep that thing down and you let it talk to the second qubit, and then the third qubit. And in this way, you keep on bringing new qubits into the top half of the system, eventually building up the entire state. And so it just happens to be true that you can indeed build up any state with entanglement entropy S using this exact procedure and a number of qubits that in this ancilla register that scale only with the entanglement entropy S. And that is meant to be just a hand-wavy argument. Obviously, it's going to be hard to see that it's exactly right if you've never thought about this before. But if you want, you can just take this as a definition of a matrix product state. It turns out that this is exactly equivalent to what people mean by matrix product states. And this has been known for some time, right? So this was actually kind of rediscovered, I would say, to some extent in 2006. Although if you go back even before matrix product states were called matrix product states, they were referred to as finitely correlated states. I think if you ask the authors of kind of the original paper on these type of states back in the early 90s, they probably would have recognized that this kind of construction is related to matrix product states. And now I just want to take one step further and just draw out the construction I just gave of kind of sequential preparation of a state as a quantum circuit, right? So it's just exactly what I just showed schematically now in this kind of circuit notation, where you have a bunch of states of your, you want to produce this state at the output of a quantum circuit. So you put in a trivial state, all your qubits in 0. And then you sweep this ancillary register, also initialized in 0, through the system, letting it first interact with just the first qubit, then with just the second qubit, then the third qubit, and so on, until it eventually is able to build up this entire state. And the claim I was making on the previous slide was just that the states that you can get out of this kind of a circuit are precisely matrix product states, which usually have this kind of diagrammatic representation shown over here on the right, where you take, so now these squares are basically a bunch of tensors where you have summations over the kind of, connected legs, and then they output the physical degrees of freedom of the wave function. And I'm not going to, I'm sure there are some people here who are intimately familiar with tensor network diagrams, and I don't need to say anything, and probably some people that never think about these things. It's not really that important to know what these diagrams mean. I just want to emphasize, if you are familiar with them, that this kind of circuit construction is kind of isomorphic to these matrix product state diagrams, and that it puts out the same class of states. The only, and the connection between them is that the matrix product state, you often talk about a bond dimension chi, which tells you, how many degrees of freedom do you sum over on these connected legs. And it's known that in general, the entanglement entropy of an MPS is limited to be logarithmic in the bond dimension. And in general, it's going to scale like the number of bond qubits in this register in this circuit construction. So basically, you can generate any matrix product state with entropy S and bond dimension chi, or chi equals 2 to the NB with just NB bond qubits and a circuit like this. And in some sense, this presents, an exponential compression over the classical case, because for a classical matrix product state, you need to scale you need to store polynomial and chi numbers in order to write down a state like this. In the quantum, in the quantum case, the number of bond qubits you need in this register, and B is just logarithmic in chi. Okay. So, if we stop there, I think we already have something kind of nice, which is, although albeit, this has been known for 15 years, at least, which is we just have a nice ansatz for how you can generate physically relevant states as a quantum circuit. But the key point I want to get across early in this talk before moving on to other things is that we actually gain a whole lot more in terms of the resources that we need to actually extract information from a circuit like that. And you can see why that would be in the following diagram. And if any of what I'm saying in this next slide doesn't make sense, I hope somebody will stop me and just ask for clarification, because it's kind of the key point of what makes tensor network techniques so powerful and so resource efficient when implemented on quantum computers. So if you want to build up a state at the output, I'm just taking a subset of the state I showed previously. So we have a circuit that kind of generates a state like this. And generally what we want to do with that state is just measure its properties, right? Like say we care about some correlation functions, which might tell us properties of the system. It might tell us the energy and how close to the ground state we are. Most useful information will be encoded in local measurements you can make at the end of the circuit. And if you look at this complete diagram, the simplification is as follows, right? If you want to measure these qubits, you can start by measuring just the first one. But notice that you could have made this measurement right here as soon as this qubit came out of this gate back here. And therefore, before in time, the bond qubit register went into this next gate to interact with this qubit back here. And what that means at kind of a implementation level is that to execute a circuit like this, you don't actually need this qubit at all, right? You could just send in the bond qubit register in this first qubit, measure the first qubit, and then stick it, reinitialize it and stick it back in here and let it serve the purpose of the second qubit. And now when you want to measure an observable on the second qubit at the output, again, the exact same story applies, right? You can make this measurement next, and you can make it way back here in time before this gate ever occurs. And therefore, it can be measured before you need the next qubit. You can recycle it, and so on, so that eventually you can measure any correlation function you want of this output state. And the only qubits you actually had to inject into this circuit were the bond qubits, and how many of those you needed depended on the amount of entanglement entropy was in the state you wanted to generate, and a single qubit that repeatedly gets measured and reused to extract information about the physical state you're generating. And so let me just redraw this in a slightly less tangled way, right? I'm just taking this diagram up here and kind of moving everything around to draw it as a more standard quantum circuit, where what I just said maybe is a little more evident, right? This circuit only involves a bond qubit register, and then a single physical qubit. And going back to the very beginning, what this construction down here on the bottom right, this simple circuit construction is actually doing is we took some complicated one-dimensional state, right? This can be the ground state of some highly kind of correlated 1D spin model or something. And, based on physical grounds, we expected it to have low entanglement entropy and therefore said it could be expressed accurately as a low bond dimension MPS. And what that means is that then we have this circuit construction, which when combined with the ability to measure qubits in the middle of a circuit and reset and reuse them, turns into a technique for making measurements on that state using only a single qubit plus entanglement entropy number of bond qubits to make measurements on essentially an infinite state. If you wanted to, you would just have to run this circuit out further and further in time to do so. And just to kind of drive home some of the connections, right? These measurements that you're making are sequential in time now in this circuit, but different times in this circuit really correspond to different places in space of this 1D state. So you're kind of mapping like the spatial extent of an infinite 1D state onto the temporal extent of now an infinite in time, in principle, if you want to carry it on forever and ever, quantum circuit. And the benefit of doing this is that there's a huge resource savings because you can simulate an infinite system with essentially no finite size effects using just a single qubit plus as many as you need in the bond qubit register to capture its entanglement entropy. And then just to remind you, we're not completely getting rid of all the qubits, right? You only need a single physical qubit to represent all these physical spins. But the kind of catch is that you need a bond qubit register with as many qubits in it as you have entanglement entropy in the state. But ultimately, my claim is that it's much better to have resources that scale with the entanglement entropy than with the system size if you want to simulate a typical physical quantum system. And here's kind of a table of how to think about this scaling. And this is fairly kind of crude, but it's like at least morally correct, I would say. And you can look, so take, for example, just the left column, this classical simulation column. And what I said early on was that, a brute force approach to just writing down the wave function, you expect to be exponentially hard in the number of qubits. And what tensor networks afford you is a set of classical techniques that are now only exponentially hard in the entanglement entropy S, which in general is much less than n. So this savings going from here to here is one way of thinking about why classical tensor network techniques are so powerful and why they have become sort of one of the leading techniques for simulating quantum systems.
Can I ask a question?
Yes, please.
Is this a fundamental limit? Like, does the entanglement entropy set like the fundamental minimum number of qubits you could be using in this, in like a image compression analogy type situation where there's like you're effectively compressing your system?
Yeah, that's a great question. And I think with suitable caveats and like not particularly onerous caveats, the answer is yes. Like that's basically the right way to think about it. Yeah.
Cool, thanks.
Yeah, thank you. Okay, so on the quantum side of this table, it's just this is the obvious thing. If you want to simulate an n-qubit quantum system, well, you need n qubits. Naively, if you just want to like fully build the state of those n qubits, so that's a logarithmic improvement over the brute force classical approach. But with these kind of like circuitized versions of tensor network techniques, you now need only entanglement entropy number of qubits, which is a logarithmic improvement over these already much more efficient classical tensor network techniques. So we expect on the quantum side, these type of techniques to lead to significant savings in actually representing and making measurements on physical states of matter. Okay, so in some sense, I gave all of this discussion just because it's simplest to introduce it this way in the context of 1D systems. And in some sense, that makes it relatively uninteresting because, classically, like I was saying earlier, 1D systems, by virtue of their very small entanglement entropy, which is generally finite or at worst grows very slowly with system size, even this 2 to the S kind of classical scaling that you get from tensor network techniques is generally really not that bad. And that's why, over the last 2 decades, matrix product state techniques, or more than 2 decades, matrix product state techniques have basically made, the kind of equilibrium physics of one-dimensional systems a solved problem in some sense. Like we now have controlled classical ways of getting, numerically exact answers about one-dimensional quantum systems. Now, I think where these techniques are really likely to play an actually important role on quantum computers is, well, there's actually a bunch of places. So one, obvious one is just don't work in d equals 1. So in more than one dimension, it's still true that people like some, state-of-the-art techniques. So this is, this is a figure taken from a paper by Steve White and coworkers where they used DMRG, which is basically, a technique for finding optimal matrix product states for 1D systems. And they took that technique and they just kind of force apply it to a 2-dimensional system that kind of is, kind of quasi 1D, like it might be longer in one direction than the other. And even though it is not necessarily a, completely tractable method for getting numerically exact answers about the kind of infinite system limit in 2 dimensions, it's still one of the state-of-the-art techniques. So at the time, at least, maybe 10 years ago, this paper had sort of the best energy estimate for the ground state of a frustrated spin model on the Kagame lattice. and provided some of the most compelling interest that there was compelling evidence that there was a spin liquid in that ground state. That said, tensor network techniques in 2 dimensions, while they may in some cases be semi-tractable or even scale polynomially in terms of the resources required, those polynomials tend to be kind of nasty. And in reality, I think there's lots of interesting places where people would love to know answers about 2-dimensional systems. And yet tensor network techniques just don't quite get you there. Like in reality, it's just very hard to make them work efficiently enough and accurately enough on a classical computer to get what you want. So I think this is a place where there's plenty of room for quantum computers to offer a potential improvement using generalizations of sort of what I just showed you on the previous slides. Another place that would work even in 1D is just dynamics, right? If you take a 1-dimensional system and you drive it out of equilibrium, there's lots of fundamental questions about the way things thermalize, whether they do or not, and the way that chaos works in quantum systems. And, moving a little bit away from kind of traditional many body physics, you might even look, for example, at photoabsorption properties of a molecule, which can be phrased as a dynamics problem for a correlated system. And all of these things rely on being able to time evolve the Schrodinger equation for a many body system, which in general will be hard even for a 1D system. And there's lots of places where, while you can apply matrix product state or tensor network techniques to studying this problem, again, as I mentioned, in more than 1 dimension, they just tend to run out of steam. And there's lots of questions we'd like to answer that we're not able to classically. Okay, so that's really the focus of this talk. The rest of it is going to be about turning the kind of construction I just showed you into an algorithm for simulating dynamics of correlated systems. I'm going to show an example in 1D, but it can be extended in principle in ways that we can chat about if there are questions to 2 dimensions. I think there's a lot of open questions about the best way to do that, but in principle, there are routes forward here. Okay, so here's how to think about, very abstractly, and then in a kind of circuit picture, what time evolving a correlated system would look like, right? So the correlated system, you won't be surprised at this point, we're going to treat it as a matrix product state. So here's the input state. And now this could be, matrix product states find use in all kinds of things, but I think probably where they've made the biggest impact is in studying correlated materials. But you could imagine this being any collection of correlated quantum systems and potentially benefiting from a matrix product state expression. And then time evolution means you just perturb this with some Hamiltonian or some unitary evolving according to some Hamiltonian. And so this could be, if this were meant to represent the state of a molecule, it might be that you're shining in a photon and you want to see, the probability of exciting an optical transition or something like that. So that could be studied by a problem of this general structure. And, it's not trivial by any means, but in general, one can take this, unitary, which is this thing acting on all of your qubits, and you can turn this into a natural quantum circuit involving just 1 and 2 qubit gates. And this is sort of a huge field called, Hamiltonian simulation, where there's all kinds of different ways with, in some cases, like provably optimal scaling of making this mapping onto a circuit. But the key point is that, you can generally frame dynamics problems as quantum circuits, where you would input some correlated state that would be nicely expressed as a matrix product state, and then it gets evolved by a circuit having just 1 and 2 qubit gates like this. And now, if what you wanted to do was actually produce the state that this dynamics led to, for example, you wanted to have it for some further quantum processing or something like that, then you would just be stuck, right? You'd have to, there's nothing you could really do to simplify this procedure. You would just have to generate this entire state at the bottom and apply all of these gates. But in general, that's not what we want to do. What we want to do is quite a bit more restricted than that, right? We might just care about correlation functions, local observables, and those amount to just appending local independent measurements on all the qubits at the output of this circuit. And so, this is the kind of thing that you would extract in any number of experimental techniques on real materials. And these kind of measurements, would encode correlation functions, equal time correlation functions. Although you could also generalize this to move some of these measurements earlier and capture even unequal time correlation functions for calculating spectral properties of the system. But the general point is that this is a fairly simple type of thing to do at the end of the circuit, and it's already enough to capture most of what we want to know about a quantum system. Okay, so the question is, how many qubits do you actually need to make all these measurements on, what did I have? 1, 2, 3, 4, 5, 10 qubits. And so the way to see the answer is to start at the top, and let's work, you can start anywhere, but let's start in the upper left corner. So the first thing you might want to do is measure these 2 qubits up here. And obviously you can't do that until they've gone through the preceding gate that happened earlier in time. So at the very least, you need to apply this gate, and you need certainly these 2 qubits at the bottom injected into the circuit. But you need more than that, right? Because before this qubit here can be injected into this gate, it has to come through this gate, which brings in this 3rd qubit over here. So you'll at least need that qubit. And again, before this 3rd qubit can be injected into this gate, it has to enter into this gate with a 4th qubit, and then so on and so forth. You can work this all the way down to the bottom. And you might say, okay, well, actually, to make these 2 measurements up here, all we really needed to do was inject these 6 qubits at the bottom in what people often call like the past causal cone of these outputs up here for the circuit. So it's basically all the qubits at the bottom that, when propagated through gates, can reach these outcomes up here and therefore impact them. But this logic actually breaks down if you have an initially correlated state, right? Because you can't just inject these 6 qubits and expect the outcome up here to be the same as if these 6 qubits were properly entangled with the rest of the system over here. And so it seems like there is no real economization in this case. You just have to have the whole input state and all of the qubits actually on hand to measure these observables. But using the techniques we just talked about on the previous slides, we know that any matrix product state input can be written as a quantum circuit. And I'm drawing it a little differently here. I'm basically taking what were previously some abstract tensors. I'm now drawing them as unitaries, where I just have some extra legs I draw with fixed qubit inputs so that they don't add any actual degrees of freedom. And these unitaries are kind of funny, where qubits come in from the left and out to the right, in from the bottom and out to the top. But this is just a rearrangement, remember, of this exact circuit that I showed you for building an MPS. So it's basically exactly this circuit, just kind of drawn in a funny way, where the bond qubit moves from left to right through the circuit, and the physical qubits move from bottom to top. And now, if you have a circuit like this, you'll see that the actual progression of this circuit is bond qubits come in, interact with this guy goes out, bond qubits go over, and then you just keep doing that through all of these gates. Eventually, bond qubits come out here. At that point, this qubit has now finished interacting with the bond qubits, which are just going to continue off to the right through this circuit. And therefore, you can actually, at this point in the circuit where the bond qubits have just passed onto this leg, you can execute all of these legs and measure these outcomes as if you had built the entire state down below. And again, the reason is that this qubit has now finished interacting with everything else in the system. Now, once you've measured these qubits, you can, again, reset them and reuse them, right? You can shove them down the bottom here and now let the bond qubits consume their next 2 physical qubits. So the bond qubits make their way through here. And now these 2 qubits can be gated up here. That means you can now execute this gate and this gate and this gate and this gate and measure 2 more at the top. And you can then reuse those qubits to do the same thing. And the point is, in this way, you could simulate the dynamics of an infinitely large 1D system starting from a correlated state. And we asked this question, how many qubits did you actually need? And the answer is you just needed these 6 qubits, plus a number of bond qubits that scaled with the entanglement entropy in the initial state in order to do this MPS construction. And so just taking a step back now to summarize kind of where things stand in terms of resources, that means you can simulate an infinitely large system using a number of qubits that scales like the initial entanglement entropy of your correlated state. That's from the bond register qubits. And then a number of qubits that scales with time, right? Because if you draw this kind of cone backwards, eventually the number of qubits that you encompass down here scales with the depth of this circuit. So basically, you need a number of qubits that's linear in the evolution time and in the initial entanglement entropy of the state. And the interesting thing is that this is kind of the typical way that entanglement entropy itself grows in dynamics, right? If you have some state with initial entropy S, and it has kind of worst case growth of entanglement, like worse that would be allowed by its kind of Lieb-Robinson light cone, it would grow linearly in time. And therefore, you'd have an entanglement entropy of this form, initial entanglement entropy plus some constant times t. And so what that's telling you is that the number of qubits you need to do this quantum simulation is actually roughly proportional to the entanglement entropy. So once again, you're taking all of your qubit resources and you're putting them not to the kind of superficially hard aspect of the problem, which is the absolute number of qubits in your initial state, but the truly kind of fundamentally hard aspect of the problem, which is the amount of entanglement entropy that's being generated by the dynamics. So it's in that sense a fairly optimal use of qubits as resources to study quantum problems. Okay. I just pause. Are there any questions at that point? I wanted to chat just probably for maybe 5 minutes about Honeywell's actual architecture, and then I'll go on to show you a demonstration of this algorithm that we made on a Honeywell quantum computer.
We don't have any questions yet in the chat.
Okay.
Maybe I could ask quickly, can you give roughly a feel for how big this ancilla register might be? Like in the previous example you just gave, like it doesn't seem like maybe that's a huge win if that register has to be several qubits and then you've saved 4.
Yeah, I can give you a rough sense. So there's no one answer to that question, but maybe I'll just give you an example that will help set the scale for this. So there are a lot of kind of known states that are low bond dimension matrix product states. So one example is a GHZ state. So if one MPS that you could input here is the GHZ state. So all zeros plus in coherent superposition, all ones. That state is a bond dimension 2 MPS. And so actually it could be constructed with just a single ancilla here. So you'd only need one bond qubit to generate a GHZ state of, in principle, infinitely many qubits. You could carry this over as far as you wanted. In general, we've done some other demonstrations where you can find, like I think you can get within kind of, a few % accuracy on the ground state of typical correlated spin chains with just of order, 2 or 3 bond qubits. You tend not to need very much. And that's really a statement about how good the matrix product state ansatz is, that typically energies converge very quickly with bond dimension and therefore kind of, exponentially faster with number of bond qubits, since that's only logarithmic in the bond dimension. So really in practice, you tend not to need very many.
I see. Okay. Yeah, that's very helpful. Thank you.
Sure. Okay. So to segue into describing the architecture, let me just point out one of the key technical challenges that I glossed over in actually doing this, which is that, measurement by its very nature, it involves coupling a qubit to its environment. You're basically intentionally introducing, a strong source of decoherence, as strong as possible. And it's very challenging to do that without accidentally decohering the rest of the qubits in your system. So you might want to just measure this qubit, but you accidentally partially measure these ones as well. And that's really a killer for this kind of algorithm, because these qubits are propagating all the information about the entanglement in the system through the circuit, and you better not touch them. So this is something that we have to work really hard to try to avoid, but it's something that actually you can do very naturally in this sort of QCCD approach to trapped ion computing that Honeywell takes. And so here's what our computers actually look like. And so this is a in-house fabricated chip that has a bunch of little electrodes. You can see it looks like a piano keyboard here. So each of these little gold spots here is an independently wired electrode that we can apply an independent voltage to. And we can, apply those voltages and change them in time in such a way that we can generate little traps above the surface for charged particles. So for us, these are ionized ytterbium and barium ions, atoms. And so we can trap them above the surface, and then we can also move them back and forth and rearrange them in order to generate kind of interactions between them that you need to implement a quantum circuit between them. And just some details, or any experimentalist would seriously object to me calling these details, but they're details from like the perspective of this talk. Our qubit is ytterbium 171, and in particular, it's this kind of clock state in the hyperfine ground state of ytterbium ion. As we, when we do 2 qubit gates between our ions, they need to be cold beforehand, and we have to achieve low temperatures for them in the middle of a quantum circuit after they've been transported, without damaging the content of this qubit down here. And that's hard to do if you directly cool on the ion itself. So what we do is we pair each qubit with a sympathetic cooling ion that gets cooled with a wavelength that the qubit doesn't really care about. And then the barium sympathetically cool the ytterbium, which helps us do high fidelity gates on ytterbium. And so the way a quantum circuit actually goes in practice is, when we want to, for example, apply a single qubit gate to one of our ytterbium ion qubits, we move it into some place where we have a single qubit gate laser passing through. It's isolated from all the other qubits, and then with very low crosstalk, we can address it and apply some kind of a single qubit transformation to it. If we want to then do a 2 qubit gate, we take 2 ytterbium ions. Notice they'd all come with barium ions clicking along to them. I just don't draw it for simplicity. I didn't draw it at all. Somebody with a lot more skills in Illustrator drew it. But you take these 2 qubits and you would merge them together into a single well. And then you can, when suitably addressing them with lasers, you can then generate 2 qubit gates between the ytterbium ions that are sharing a well here. And the beauty of this is, a little more schematically, we can bring ions very close together in order to implement very high fidelity entangling gates. And then we can move them apart dynamically and then apply measurement to a single qubit. And by spatially separating these, we greatly reduce the crosstalk of these measurement and reset beams, so that we're able to measure this qubit without scattering any light at all off of this qubit, which is exactly the condition we had to satisfy, I was saying, to implement a circuit like this. And in general, I guess I'd like to point out that this technique is something you need much more broadly, right? I mean, in the future, we all hope eventually to be doing quantum error correction on quantum computers, turn them into something actually useful. And quantum error correction in most incarnations involves measurements in the middle of a circuit that are non-destructive to unmeasured qubits, and then the possibility of applying corrections based on the classical outcomes of those measurements. And actually, there's a nice demonstration by the theory group at Honeywell recently. If you're interested in, you can check out this archive post about implementing the color code using exactly these kind of techniques. Okay.
Sorry, Mike, can I ask a quick question?
Sure.
So there are a few ways to do these kind of mid-circuit measurements. I'm wondering why, so instead of just like separating all the other guys that you don't want to be hit with your light, in principle, you could do like a QND type entanglement with the barium ion, or you could use like metastable shelving states or something in ytterbium.
Yeah.
Just wondering if there's a clear answer why this way is the preferred.
Yeah, it's a good question. So I would say you've pretty much nailed it in that the 2 things you added to the list are kind of the other 2 of the 3 key technologies that, going back to like the early 2000s, people at NIST and then Innsbruck and Oxford and other places demonstrated for doing low crosstalk measurements. So just like you said, you can shelve or you can do QND. In principle, we could do that with the barium ions. All of those things have additional challenges, right? Shelving requires other lasers and has limitations to fidelity as well. QND can be limited by some aspects of your 2 qubit gate fidelity, which can also limit the measurement fidelity. So in reality, the best way to do this is probably a combination of all of those approaches, or some combination of 2 of the 3 of those approaches. It's just that for us, we already need to be able to do this transport in order to do, to gate any 2 qubits in our architecture, and also to do single qubit gates with low crosstalk. So this is something that we're already kind of stuck doing. And so it's sort of, in some sense, we get it for free. We're able to reduce crosstalk this way automatically. But we could do the things you're talking about in principle in the future to improve it further.
Okay, thanks.
Mm-hmm. So the actual computer that we used for a demonstration of this technique looks like this. So it's designed with 5 gate zones, of which in this demonstration, only 3 were actually active. And actually, I only drew 10 qubits here, but I think for this demonstration and this data, the number of qubits you shove into this is not really a question of trap design so much as a question of like, understanding the correct, voltages to apply to the electrodes to put wells exactly where you want them. So you can put many ions in principle into this trap. And we used 12 qubits, so 12 ytterbium and 12 barium ions loaded into this trap for this demonstration. In these and they're always kept in these 4-ion crystals where the qubits are on the outside, the cooling barium ions are on the inside. we cool prior to 2 qubit gates in order to achieve pretty high fidelity. So the 2 qubit gate fidelities in this trap at the time this work was done were kind of in the ballpark of mid to high 99% fidelity. So not quite 99.9, but kind of pushing in that direction. Much higher fidelity single qubit gates. And the important point for this demonstration is that the probability of accidentally measuring another qubit when you measure a single qubit is something less than about 5 × 10⁻³ So it's kind of at worst comparable to the 2 qubit gate errors. But in general, actually, it's probably quite a bit less than this. It's somewhere between kind of a couple E-4 and 5 E-3, depending on exactly where you are in the trap. And there's details of all of the techniques that we use to actually achieve this in this archive post down here for people that are interested. Okay. So the model that we chose to study as a starting point to demonstrate this algorithm is what's called the Kicked-Ising model. And I don't want to go into a lot of details. I'll say in just a minute why we chose this model. It has some nice properties that actually made it a really nice test of this algorithm. But basically, the story is, if you're familiar with the quantum Ising model, which involves these kind of ZZ Ising interactions between nearest neighbor qubits in a line, which cause the energy to be lower if those qubits point in the opposite direction, and then it has a transverse field, which for this Kicked-Ising model, instead of leaving the transverse field on, you just pulse it, right? So it's this sum of delta functions. So at alternating layers, you have evolution under this Ising interaction, and then sudden kicks by this transverse field that rotate your spins around the x-axis. And then you also have a longitudinal field, which in general is needed to make this model non-integrable. So at h not equal to 0, you expect the dynamics of this model to be chaotic, or I could just say thermalizing. So it should eventually just kind of randomize any initial state and generate an infinite temperature state.
Mike, real quick.
Yep.
Paul is asking if you can comment on the gate speeds, gate times.
Yeah. Sure.
He's also asking how long it takes to do the ion shuttling.
Yeah, great questions. The gate times are relatively fast compared to the other two things you asked about. The gate times are kind of, they vary actually depending on the exact system, but they're in the ballpark of like a few tens of microseconds. Those are typical 2 qubit gate times. Single qubit gates are faster. The actual dominant time spent in executing a circuit like this is from transport, like you said. So the typical time that it takes to rearrange all of, so say you gate, like these pairs of qubits, and now you have in the next layer of your circuit gates between other pairs. So you need to completely rearrange how these ions are paired before reapplying the next 3 gates. That time scale is in the ballpark of a few milliseconds. That's sort of the total transport time. But that's transport involving many, many, many primitives, right? Where you're splitting wells apart, you're swapping crystal orders by rotating these things off of this center line, and then you're linearly transporting them between different zones. So the sort of total sum of all of those transport operations for a typical kind of random rearrangement of qubits is in the couple, or a few millisecond ballpark. Does that pretty much answer it?
Yeah, I think. Yeah, Paul, go ahead.
Yeah, thanks. That's great. The last question is, how long does it take to do the readout in this case? Because of course that depends on how many photons you need to collect.
Oh gosh, that's a good question. I don't actually remember the number. I'm going to guess, and I don't think I'm off by an order of magnitude. I'm going to guess it's 100 microseconds.
Okay. So the shuttling is definitely the slowest part.
Yeah, the slowest thing is the shuttling, and then also actually the cooling takes quite a long time prior to 2 qubit gates. So it's kind of roughly, those are the 2 bottlenecking things.
You can't cool while you're doing the gates since you're doing it sympathetically?
You can Doppler cool while you can't cool actually during the gates. You can cool during the transport, and we do cool during the transport. But unfortunately, getting to the temperatures you need for these kind of gate fidelities requires sideband cooling, and that's really only possible to do once all the qubits have gone to their assigned locations.
Yep.
And that's kind of the bottleneck.
Great, thanks.
Yep. Okay, so yeah, I think I'm almost done here. Actually, I mean, what I'll show you for this demonstration is relatively short. I might breeze through a couple of these slides because they're not like super important for the point I'm trying to make. But so anyway, this is the model we studied. It turns out that this has a known mapping onto a quantum circuit that's exactly of the form I just showed. So in general, for arbitrary matrix product state inputs, you can glue them together with this kind of brickwork, alternating like even odd layer of 2-qubit gates, like I'm showing. Let's see, actually, let me not say anything other than that. It's just that like this model maps nicely onto a circuit of the type that I said we could simulate using these qubit reuse techniques and matrix product state ideas. There's one special point about this model. We studied it at a special point in parameter space where it has kind of a hidden symmetry, which can be understood in terms of what people call dual unitarity. And what it really is for special values of the transverse field, and the Ising interaction strength. These gates, so normally we think of a unitary gate as some gate with an implied direction, right? It ingests qubits and it spits them out. So it evolves in time and not, for example, in space from left to right. And diagrammatically, that means if you take U and U dagger kind of summed up along the time direction, it produces the identity matrix. So it does nothing in time to your circuit. And at this special dual unitary point that we work, these gates actually are unitary even when read from left to right. And you can kind of think that as just a statement. You can think of that as a statement that they generate evolution in time, and they also actually generate evolution when read from left to right in space. Honestly, none of that is super important. The reason we chose this special point is just that it turns out, so while the techniques we're relying don't rely on that symmetry, it's really nice because, first of all, it lets you calculate almost anything that we would like to calculate. So it's known from this work, also a lot of other related work actually on this, that you can exactly calculate correlation functions, even starting from some classes of initial matrix product states of models when they have this dual unitary symmetry. So this gives us a nice kind of foot in the door to do classical checks of the output of these circuits. The other nice thing about these dual unitary circuits is that in some sense, they're kind of a maximally hard test for this technique or for a quantum computer, because they generate entanglement at the maximum possible velocity. And I'm showing plots from a couple different papers by Austin Lammerkraut's group, where you can see that correlations tend to be kind of confined to this light cone edge, which you can think as meaning that entanglement is basically growing as quickly as it's allowed to by the Lieb-Robinson bound. And also, despite being solvable, these circuits have a lot of very generic properties. So they're not so finely tuned that you'd expect them, for example, to be amenable to some technique that wouldn't be amenable more generally. So they're just a nice, kind of fairly robust and fairly generic class of models that really stress this algorithm, and that nevertheless we can make easy classical comparisons using exact techniques. And I'll just show you, let me just skip over this in the interest of time, because I do want to have like a few minutes left if there are more questions. So let me just, I'll just say very quickly that we're taking this kind of a time evolution circuit that you see on the left, and we're implementing exactly the dissection of this into a quantum circuit with reuse that I talked about. So we're first implementing this kind of upper triangular causal cone of the first qubit at the output in some circuit that looks like here on the right. And then we sequentially add slices to build up the entire output of, in principle, an infinitely large system if we run the circuit long enough. And the number of qubits you need scales like the time, even for an infinite MPS. It's independent of the number of qubits in the MPS. Okay. So the experiments we ran, what we measured were just transverse correlation functions to try to understand the agreement between this procedure and exact calculations of these correlation functions. And we studied this as a function of a range of spatial separations R and time evolutions T, actually going up to T equals 8. I think this is a typo. But the important thing is that the reason we like this technique is that despite having all these simplifications and using very few qubits, and despite the fact that you never at any one point in time actually have the output state, it never actually exists, you can nevertheless infer very useful things like correlation functions that you would normally think of as kind of the bread and butter of many body physics, what gets measured by standard techniques in many body physics. And so in the example we ran, we didn't run the circuit forever. We ran it for some finite time, which meant we only produced an MPS of some finite spatial duration. It turned out to be about 32 spins, or actually 39 spins at the input. We sliced up the circuit like this, and that gets turned into some circuit that just continues, each one of these layers is a new slice, and we build up the space spatially in time throughout this circuit. And let me just kind of finish up by just making the point that not only can we simulate large systems with essentially no finite size effects using a relatively small number of qubits. So we only used 11 qubits for this data, despite the fact that we were representing almost a 40-state matrix product state. But we also can do it in a way with high enough gate fidelities that we get really nice quantitative agreement with theory. And this is just another way of looking at the correlation plots that are kind of, color plotted here against space and time. Here, I'm just plotting each horizontal slice as an independent curve shifted up in time, just to show you that there really is pretty good quantitative agreement within the error bars we can achieve with kind of reasonable shot noise in a reasonable amount of runtime. And this is real, and yeah, basically, sorry, I'm running out of time, so never mind this. It's not really important. I'll just say in closing that, not only do we see generally good quantitative agreement, it's good enough that we can actually extract kind of the relevant physics that you expect to happen in this model. So one feature of choosing a non-integrable point of the model where you expect thermalizing behavior is that correlations don't live forever along the light cone. They should decay exponentially. And we can actually measure these correlation functions along the light cone at different parallel slices and see that this data really agrees with the exponential decay plotted in these dashed lines using these exact kind of tricks for dual unitary circuits. So we're actually able to sort of quantitatively see the relevant physics that we want to see in this relatively large 1D system undergoing non-equilibrium dynamics. Okay, so with that, I will wrap it up. And I think instead of saying anything about the outlook, since there's like 1 minute left, I'll just stop. Thanks.
All right, thanks for the great talk. Let's see, we have one question here. I think at this point we can let the participants chime in if they want to ask a question. So maybe Lucas, feel free to ask your question.
Yeah, hi, Michael.
Hey.
I just had a question about the time evolution for your quantum circuits.
Okay.
So I was wondering if there's a way to compress the time evolution circuit in a way that still maintained the advantages of the MPS.
That is a great question. So I would say we have some vague ideas about how to do this, although I think it has many of the usual challenges of kind of variational techniques. It would probably have to be done variationally. I suspect the reason you're asking this is that, in actual like classical tensor network based dynamic simulations, typically what you do is for some, trotterized evolution, any given layer of gates introduces only a little bit of entanglement. So you're constantly, it doubles the bond dimension, and then you kind of reduce that bond dimension through a compression step to keep the calculation from getting out of hand. And we would love to be able to do that quantumly as well. I think there are routes to doing it, but it's not entirely clear to me whether they're actually feasible, honestly.
Okay.
So it's still an open question. I think the one thing I will point out, though, is that, at least in the types of kind of circuit dynamics problems that we were studying, like this Kick-Deising model, it really maps onto a circuit where the gates are not like infinitesimal time evolution that are weakly entangling. They're really like maximally entangling gates. And therefore, there'd really be no benefit in that context to compressing. So you kind of get away for free without having to do that.
Okay.
But yeah, in general, it'd be a really nice thing to figure out. And I think there's plausible routes forward there, but I don't know for sure.
All right. Thank you.
Yep.
All right, any last questions? All right, well, let's thank Mike again.